Hello and welcome to the sixth week of lectures of this course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this week, we will look into fuzzy inference systems, which are the mainstay of this course. Specifically, we hope to look into fuzzy relational inference. However, even for a simple fuzzy inference system, there are many building blocks, and unless we understand these components in some detail, it is difficult to build a useful fuzzy inference system. In that quest, we will look into fuzzy propositions in this lecture. We will begin by recalling what is approximate reasoning. Approximate reasoning, as we will understand and explore in this course. We will look at a schematic diagram of a fuzzy inference system. We will look at some different interpretations of fuzzy sets also. And finally, we will look into fuzzy propositions from different perspectives. Well, what is approximate reasoning? We have seen already in one of the earlier lectures that if you are looking at the reasoning process itself, you need two things. First, the knowledge about the domain in which you are going to do the reasoning, and also the intelligence to apply on this knowledge to reason. Typically, this knowledge is given or represented in the form of conditionals. If you look at classical reasoning, we might have a piece of knowledge in the form of this conditional, which by now must be extremely familiar to all of you. If f is differentiable, then f is continuous. Now, given this piece of knowledge and a function f of x is equal to x square, we know it is differentiable, the function x square is differentiable. Then we ask the question, given this piece of knowledge and expressed in the form of conditional and this new input, once again it is in the form of knowledge that f of x is equal to x square is differentiable. What is it that we can infer from the general piece of knowledge that we have and a specific piece of information? And we see that from these two we can actually infer that f of x is equal to x square is continuous. Now, what gives us the backing to do such an inference or reasoning? We know that there is a rule, a mathematical principle called the classical modus ponens, which says that if A implies B and A, then we actually can infer B. Now, think of the same piece of knowledge given to us in terms of the conditional, but now we have the function f of x is equal to mod x. Now, if you ask the question, is it differentiable? We all know that if you consider the domain of this function, the entire domain of this function, which is R, then except at the origin, everywhere else it is differentiable. So in some sense, colloquially speaking, you could say it is almost differentiable. The question is, given this piece of knowledge and this new information, can we infer something? Well, classical modus ponens does not allow us to infer anything. Note that we should also point out something very important here. The given function f of x is equal to mod x, the new piece of information, right now does not exactly fit into the space about which the antecedent is expressing. If you recall, in the case of implication, we said that if antecedent is false, then the truth value of the conditional is always true. But here, note that we are not talking about the truth value of the given piece of knowledge. That is a given. Now, using that piece of knowledge and a new piece of information that has come into existence, we want to do some inference. So now, in this case, that is where we see that the piece of information that we have newly obtained does not exactly match the antecedent of the given rule, which actually contains the knowledge that we are considering within this domain. However, if you look at what we call common sense reasoning, we would perhaps like to come up with such a reasoning that mod x is almost continuous. Of course, as was mentioned earlier also, we know that mod x is actually continuous, but given this piece of knowledge and this information, what best could we infer? Now, this is something that we could probably infer. Now, let's go back to the folklore example that we have discussed in one of the earlier lectures, just so that we will fit this in the form of fuzzy if-then rules. Now, with the knowledge of fuzzy set theory, perhaps this rule will make more sense to you. We have this rule: if the tomato is red, then it is ripe. Now, we pick up a tomato and it is greenish red, and we nonchalantly make the inference that tomato is not yet ripe. So what is the difference between classical reasoning and approximate reasoning? Well, we still have a conditional in the form of A implies B. We are given an A dash, which is typically not identically equal to A. And we still would like to make some reasonable inference B dash. This is called generalized modus ponens. And once again, we will look at performing approximate reasoning in the framework of fuzzy set theory. That means the A's, A dashes, B's, B dashes, all of them that we are going to discuss are all fuzzy sets. Well, with this quick recap, let's go to look at how a general schema of fuzzy inference mechanism will look like. Now, we know that even when we are dealing with a computer or a calculator, this is essentially the setup. So we give some input, it does some processing and gives us an output. Now, to do this processing, it will depend on two essential components. These are the data and the intelligence. So now, data could be some supplementary data that is required for processing the input, or it could also be data about the data, which is metadata. So in that sense, you could say it is also the knowledge. Now, processing means we need to process input using this intelligence, but of course, the intelligence has to talk to the knowledge. It has to interface with the knowledge so as to obtain some meaningful outputs. Now, in our case, the same thing happens. We are being given an input and we want an output, and in the place of knowledge, we have actually captured this knowledge in the form of fuzzy if-then rules, and we are going to apply intelligence on this. Intelligence is in the form of an inference scheme. So these are the two important components when you are talking about any inference scheme: the actual algorithm itself, how do you infer, also how the knowledge is stored, so that given an input, based on the knowledge, this inference algorithm can act on it and give us a meaningful output. Here, the input and the output typically will be fuzzy sets, but we can also take them as points from classical sets. We'll come to it when we deal with fuzzy inference systems, perhaps in the third or fourth lecture of this week. So typically we give an A dash and we are expecting B dash. Now, to be able to understand this general schema, a few concepts need to be explored and understood. Firstly, we are talking about knowledge being captured as if-then rules, as fuzzy if-then rules. To be able to understand this, we need to know how classical if-then rules themselves look like and how are they interpreted. By classical if-then rules, we mean rules where the antecedent and consequent sets A and B are actually classical sets, subsets of the corresponding domains. For instance, it might look like this: if X belongs to A, then Y belongs to B. From here, we'll move into fuzzy if-then rules, where the antecedent and consequent sets are actually fuzzy sets over some appropriate domains, and the rules themselves would look like this: if X tilde is A, then Y tilde is B. So if tomato is red, then it is ripe. But towards understanding these things, we need to understand also the individual components of the rules. X tilde is A, Y tilde is B. So these we call as fuzzy propositions. So to understand them, we need to see how they are interpreted and what are the perspectives they offer us. So in that sense, we also might want to look at fuzzy sets and try to interpret them also in a different way. So in this lecture, our main focus will be on understanding fuzzy propositions. In the next lecture, we will look at fuzzy if-then rules. And with these two basic building blocks, then we will be in a better position to discuss fuzzy inference schemes. Well, let's look at fuzzy sets themselves. The first perspective of fuzzy set is as a membership function. It talks about the belongingness of an element to a concept. So we know that mathematically a fuzzy set is a function from an underlying domain X to 0, 1. Visually, we indicate it in terms of a graph of such a function. And we know that it actually captures or represents a concept. Hot, very hot, cool, high, medium, average, fast, slow, costly, cheap. These are the concepts that we try to represent using a fuzzy set over an appropriate domain X. Now, let's look at one particular example which we have seen earlier too. We want to represent the concept points close to 0. Now, let's limit the domain to be just the -1, 1 interval. And then this could be one way of representing this concept. So now as you move away from 0, obviously the membership values start to taper down. And in this case, they taper down in a linear fashion. And now if you take the value 0.3, then you are essentially asking to what extent 0.3 is close to 0. This is well known. So this is of how often a fuzzy set is thought of. But we can also offer a different perspective of fuzzy sets as a possibility distribution. What do we mean by this? Let's begin with a probability distribution. We know that if you are given a random variable R, associated with that is either a PMF, probability mass function, or a probability density function. Now, if you take a value x0 from the domain X and ask this question, what is the probability that R could be x0? Then this probability is essentially P of x0 if it is a PMF, if the domain is discrete, or if you have a continuous distribution, probability density function, then this is how you calculate the probability around that point x0. How is it interpreted? It is interpreted as the probability of x0's occurrence. Now, when we are talking about PMF or PDF, note also that this property of it being normalized is available to us. Let's stay with this probability distribution for a few minutes more. Let's construct a probability distribution of points near 0. That means come up with a PMF or a PDF about how the probability of points near 0 could be distributed. One way to do it is kind of use a Gaussian membership function, and if you are band limiting the domain, then you could also truncate the Gaussian. So let's once again fix the domain to be -1 and 1, and that's where we are actually sampling the points from. And we want to sample points in such a way that they are actually being represented, they are close to 0. So now let's think of this tapered or truncated Gaussian. Now this is one way to look at this distribution. The corresponding PDF could be given like this. But we could also consider the earlier fuzzy set, the triangular fuzzy set that we considered on this domain also as a PDF, because the area under the curve is 1, and so this could also be considered as a possible PDF. So this gives a different distribution of the points that are close to 0. Whereas when you sample from this distribution, the probability with which you get 0.3 is different from how you would get with some other distribution. One point that we need to immediately note is this. Look at this. We are considering the same function. These are two graphs of the same function, but on the left hand side and the right hand side, we are interpreting them differently. On the left figure, we are interpreting it as a fuzzy set. On the right side figure, we are interpreting it as a probability density function. Now, if you look at 0.3, both these values, what are we asking here with 0.3? when it is represented as a fuzzy set, when it is considered as a fuzzy set, we are only asking the question, to what extent does 0.3 belong to this fuzzy set? But now, when it represents a PDF, what is it that we are asking? Well, note that probability of R is equal to 0.3, because it's a PDF, has to be taken around a small interval around 0.3, and the area under that is assigned as the probability. Now, the interesting thing is, we need to understand what is it that we are asking. What are we asking? Are we asking this question, what is the probability that 0.3 is close to 0? No, this is not the question we are asking. What we are asking here is, given x0 is close to 0, you have sampled a point, and we know that that point comes from the distribution, and it is from the distribution R, which is actually capturing the concept of points being close to 0. We are asking the question, given x0 is close to 0, what is the probability that x0 is equal to 0.3? As you see, as you go closer to 0, the probability of sampling points closer to 0 are quite high because of this distribution. So this is the question that we are asking in when you are in the framework or the setting of probability. But now, instead of looking at this as a probability distribution, let's go back to looking at it as a fuzzy set. And now we will say we are looking at a possibility distribution of points near 0. What do we understand by this? We are not asking the question to what is the probability that 0.3 is close to 0, but we are asking the question, to what extent is 0.3 close to 0? So you will see that between this and the earlier, the thick band around 0.3 has actually become a thin line, because we are only fitting the value 0.3 into the function and finding it out. So to what extent is 0.3 close to 0? Now, when this is the question that we want answered, then essentially we are looking at R tilde as a membership function. We are discussing the belongingness of 0.3 to this concept. But we can also ask the same question. Given x0 is close to 0, what is the, instead of probability, we can ask what is the possibility that x0 is 0.3? We have picked up an x0 which is close to 0, and we can now ask what is the possibility that x0 is 0.3? If we were interpreting fuzzy sets like this, then we call that a possibility distribution. So we can look at fuzzy sets also as possibility distribution. So these are two ways to look at fuzzy sets, either as membership functions or as possibility distributions. Now let's look at fuzzy propositions themselves. Once again, we will see that there are many different interpretations and perspectives possible here. Now, to begin with, what is a classical proposition? Crow has a beak. Rahman is a musician. Einstein is a scientist. Now, these are propositions. Why do we call them propositions? They are declarative statements. Their truth value can be determined. Either they are true or false. In that sense, essentially, a classical proposition is nothing but an assertion. We should also note what is not a proposition. A question is not a proposition. What is the time now? That's not a proposition. We cannot ascertain its truth value. Similarly, a rhetorical question is again not a proposition, nor is an exclamation a proposition. So proposition is an assertion whose truth value can be determined. Now, what is a fuzzy proposition? We say temperature is hot, pressure is high. So these are fuzzy propositions. Essentially, we have a statement of the form x tilde is A. Now, what is A? It's a fuzzy set. What is x tilde is A? This is what we want to interpret now. Question is, how do we interpret this statement, this assertion, wherein we have x tilde is A and A is a fuzzy set? Let's look at that. Perhaps beginning with an example. So once again, we have a fuzzy set A on an appropriate domain X. And the question now is, how do we interpret x tilde is A? Take this example, John is tall. Clearly, tall is a fuzzy set, a function from the set of heights to 0, 1. Perhaps we could also fix the set to be 0 to 7 feet, the interval 0 to 7 representing feet to 0. So now John is tall clearly falls under this category, and we could call it a fuzzy proposition. Question now is, how do we interpret it? The first interpretation is that of determining the truth value of the statement. And how do we do this? The question is, we are given x tilde as a. One way to interpret it is as the truth value of this statement itself. Let us be given an x naught, and let's know that x tilde is equal to x naught is actually known. Remember, it is known that x tilde is x naught. Then we say t of x tilde as a is actually equal to a of x naught. What is t here? The truth value of the statement x tilde as a is in fact equal to the membership value of x naught in a. So essentially, we are stating to what extent the statement x naught is equal to x tilde is equal to x naught is a is true. So we are finding out the truth value of this statement given x tilde is equal to x naught. In terms of our example, we have this fuzzy proposition, John is tall. Now we know that John is 5 foot 10 inches. That means x tilde is equal to x naught is 5 feet 10 inches. Now this is the truth value we assign to this statement, this fuzzy proposition. To what extent is John tall? The truth value of John is tall is essentially to what extent 5 foot 10 inches belongs to this fuzzy set tall. If it belongs to the degree alpha, then that is the truth value of this statement given x tilde is equal to x naught. So this is one way to interpret a fuzzy proposition. Essentially, we are evaluating the truth value of the statement itself based on precise information. There's an alternate interpretation also, a second interpretation, that of determining the compatibility with respect to the given fuzzy proposition. What do we mean by this? Once again, we want to interpret x tilde as a. Now, earlier we were given x tilde is equal to x naught. It was known. Now, let's assume that x tilde is x naught. Then what does the statement say? Then a of x naught, remember a is a fuzzy set, a of x naught is its membership value. It gives the possibility that x tilde can assume the value x naught. So now this goes back to the second type of interpretation that fuzzy sets can be given. So this membership value can be looked at as the possibility that x tilde can assume the value x naught. Once again, for the case of our example, John is tall. Now we do not know the height of John, but we are asking the question, what is the possibility that John's height is 5 foot 10 inches? So now this alpha, which is the membership value of 5 foot 10 inches in this fuzzy set tall, represents that possibility that John's height would be 5 foot 10 inches. So now, once again, we are evaluating something about the statement, the possibility that John's height is this, based on imprecise information. We actually do not know x naught. There is also another way to interpret fuzzy propositions as assignment of linguistic values. What do we mean by this? So now, for this particular case, we have actually color coded the statement x tilde as a. Now, look at in typical programming languages, computer programming languages, we declare variables of different types. So when we write such a statement, int I is equal to 10, then the compiler understands that I is of type integer, it's an integer variable, and it can assume values only from the set of integer values. If you give it a real, of course, it knows how to truncate it. So I is an integer variable, can assume integer values. Float u is equal to 3.14 means u is a real variable, it can assume real values. If you say bool b is equal to true, so we are initializing, then it understands b is a bool variable and it can only take either true or false. It cannot take 3.14. Of course, some compilers may be truncating and understanding what it is. Perhaps if it is not 0, it may be giving the value 2. Anyway, the point is you have a variable, and the moment you declare that variable to be of particular type, then it knows that it can only assume values from the corresponding domain. Now, let's consider this statement. Pressure is high. It is much like a specific case of x tilde is A. So high is A, fuzzy set defined on an appropriate domain, and pressure is x tilde. Now, what we can interpret this x tilde is A to be is as follows. X tilde can assume the value A. That's all that we are saying. X tilde can assume the value A. So if you were to give such an interpretation, how do we understand x tilde to be? So let's stay with this. Now, once again, x is the underlying domain. We call x tilde to be a linguistic variable. And A coming from f of x, which is a fuzzy set, we say it's a linguistic value. So x tilde is the linguistic variable and A is the linguistic value that it can assume. Now, in this case, A was high, but A could as well be low, which is again a fuzzy set defined on x. It could be medium, another fuzzy set defined on x. Now, note that when we say x tilde can assume the value A, so we are somehow interpreting and essentially keeping the semantics of x tilde with respect to the context as a fuzzy set defined on x. You could also say, can A be cheap? Pressure is cheap. Or can A be fast? Pressure is fast. But as long as you have a decent way of interpreting these fuzzy sets, it is okay. But otherwise, we need to keep the context in mind. And it goes back to one of the earlier lectures where we said the context has to be kept in mind while defining the fuzzy set. But now the context also has to be kept in mind while choosing the set of linguistic values a linguistic variable can actually assume. So what we have is x tilde as A can also be interpreted as assigning a linguistic value to a linguistic variable. X tilde can assume the value A. The most important thing is x tilde is equal to A and it is coming from f of x. In the context, with respect to the context, we have fixed the domain x and we will interpret by giving semantics accordingly so that x tilde is equal to A or x tilde as A makes sense in that context. Well, a quick recap. We recalled generalized modus ponens. We saw a couple of interpretations of fuzzy sets. One of them which we already knew, which was that of a membership function, but we saw that it could also be seen as a possibility distribution. And clearly, the distinction between a possibility distribution and a probability distribution was explained. And we saw fuzzy propositions, and we again had at least 3 different interpretations. First of them enabling us to discuss the truth value of the statement itself if x tilde is precisely known. If x tilde is not precisely known, then we could look at it as possibility of x tilde assuming that value, essentially going back to the second interpretation of fuzzy sets. And finally, we also looked at it as a linguistic variable assuming a linguistic value. So with this, the basic building block of fuzzy propositions, which go into building a fuzzy if-then rule, has been explored to perhaps a sufficient detail or what is required for us. In the next lecture, we will look at fuzzy if-then rules. Now, this is an excellent edited volume by Bestek, Dubo and Prade. For more on the topics dealt with in this lecture, you could refer to this book, as also to the papers of Dubo and Prade, one of them being 3 semantics of fuzzy sets, and also an earlier paper of Frank Lavon, which deals with some of the things that we have discussed, fuzzy sets and vague environments. In the next lecture, we will discuss fuzzy if-then rules. With that, the basic building blocks of fuzzy inference system must be in place so that we can look into fuzzy inference systems. Glad that you could join us for this lecture, and looking forward to seeing you soon in the next lecture. Thank you once again.